Hi everyone, I Ritvik Bhadra, Assistant Professor HIT Kolkata, welcome you to my lecture number 5, which will be on my buck boost converter. A buck boost converter is also called as a step up down chopper. That means it can either operate in step up mode or in step down mode. The mode of operation depends upon how you choose your duty cycle D. We'll make the analysis of this kind of converter in the same way as we have done of buck converter or boost converter. First, we'll understand the operation of the circuit, draw the relevant waveforms, and then at last derive all the necessary equations related to buck boost converter. So let's get started with the topic. So we have drawn the basic circuit of a buck boost converter. It consists of a DC voltage source termed as Vi, a single pole double throw switch with fixed point S and two throws A and B, an inductor, a capacitor and a resistive load. Now again we have to take the same assumptions, that is all the current directions and the voltage polarity marked in the diagram, that is for IL, IC, I0, VL and V0 are treated to be positive. And if you observe a small difference in the diagram, if you compare with the boost converter or a buck converter, the load polarity has changed. That is, the load current enters at the bottom and leaves from the top, whereas in the other two circuits that we had studied, I0 was entering from the top. Since the I0 enters from the bottom through the load, that's why the lower terminal of the resistance is plus and the upper terminal is minus. So we will be analyzing the circuit now, and we will be drawing the waveforms on the right hand side, which consist of VL, IL, IAS, etc. So let's start with analyzing the circuit. During the DT period, you know your fixed point S will be connected to A, hence our circuit will be looking as follows. The voltage source Vi gets connected to the inductor and the inductor starts charging with current flowing through the loop in the clockwise direction. With the direction of current flowing as shown in the diagram, the upper terminal of the inductor is positive and lower terminal of the inductor will be negative. So now what we will do, we will apply KVL in the clockwise direction. So Vi minus VL gives you 0, so VL is equal to Vi. And since Vi is an input DC voltage which is constant, so VL will also be a constant value with magnitude Vi. Next what we will do is draw the value of VL during the DT period in our waveform. Thus next what we have done is drawn the waveform of VL, which is nothing but a constant DC voltage which is Vi during the DT period. Next, calculating the value of IL. As you know, IL general equation is equal to VL by L into T, and during the DT period VL is equal to Vi. So IL is equal to Vi by L into T, and Vi by L indicates positive slope. So if I am drawing IL, it will have a rising slope of Vi by L or a positive slope of Vi by L. So next what we will do is draw the IL waveform. As you can observe on the board, the IL waveform is already drawn having a positive slope of Vi by L, and we have considered a continuous current. So inductor current is not starting from 0, it is starting from some height during the DT period. Next we will calculate the value of IAS and IBS and then plot the waveform for IAS and IBS. If you observe the diagram drawn on board, the current from A to S is nothing but the inductor current IL, which we had already calculated as Vi by L into T. And since B point is not connected to S, no current will flow from B to S, hence IBS has been treated as 0. Hence I have drawn IAS, which is looking same as IL, that is having a positive rising slope of Vi by L, and IBS as 0 by making the x-axis bold and writing 0 during the DT period. Next, going into calculation of VAS, which is the potential difference between A point and S point. So VAS can be written as VA minus VS, and if you observe the circuit, A and S point is short circuited, hence A point and S point will have the same potential, thus VAS will be 0. Thus we have represented VAS as 0 by making the x-axis bold and marking it 0 during the dt period. Next, we'll calculate the value of VBS. For your understanding, I have already drawn the B portion. So, as we have seen that A point and S point are short circuited to one another, or that is they are having the same potential. So, VA is equal to VS is equal to the source voltage VI. And since B point is connected to the negative of the load voltage V0, VB will be minus V0. So, VBS can be calculated as VB minus VS, that gives you minus of Vi plus V0. So, next what we will do is plot the value of VBS on the waveform. Thus, what I have done is represented VBS as minus of Vi plus V0 during the dt period, and since Vi and V0 both are constant DC voltages, so VBS will also be a constant DC voltage but having a negative sign. Hence, VBS is shown negative. So, our first period of study during the dt period has been over and we have drawn all the relevant waveforms. Now, we move on to the next period of study, that is the 1 minus d into t period or the t off region. During this period, the S point is connected to B and the circuit looks as follows, or what is drawn on the board. The inductor current remains in the same direction, but however, when the inductor discharges, its polarity changes. So, the voltage across the inductor has upper terminal negative and lower terminal positive. Next, we apply KVL in the circuit. What we will get? VL minus V0 is equal to 0. So, VL comes equal to V0. So, I have represented VL as V0 but in the negative direction during the 1 minus dt period. Since V0 is a constant DC voltage, the value of VL during this period is plotted parallel to the x-axis. Next, we are calculating the value of IL, which is nothing but minus V0 by L into T. The minus indicates that it is a negative slope or a decreasing slope. Thus, the representation of IL during the 1 minus dt period in the waveform is shown a negative slope of minus V0 by L. Then we will find out the value of IAS and IBS during this period. As A point is not connected in the circuit, IAS can be treated as 0, and IBS, if you see the circuit only, the current flowing from B to S is nothing but inductor current IL. So, I have represented IAS as 0 by making the x-axis bold, and IBS is nothing but IL, which means a decreasing slope of minus V0 by L during this T off period. Next, we will plot the voltage VBS. As you can observe, the circuit S and B point are short circuited, so both will have the same potential, hence VBS will come out to be 0. Thus, VBS when represented in the waveform, I have marked during this 1 minus dt period as 0 by making the x-axis bold. Next, we will plot the value of VAS. As A point is connected to the positive terminal of the input DC voltage VI, so VA is equal to VI. B and S point are shorted and B point is connected to the negative of the output voltage V0. So VB is equal to VS is equal to minus V0. So VAS comes out to be VI plus V0. Thus, here I have represented VAS as VI plus V0 during this T off region or 1 minus dt period. As Vi and V0 are both constant voltages, VAS will also be a constant value. Hence, it is represented as a straight line parallel to the x-axis during this period. Thus, I have completely explained the operation of a buck boost converter and also drawn all the relevant waveforms. Next, what is the average value of the inductor current? If you observe the circuit, S is now connected to A and IL average is nothing but the source current IS. Now, S is connected to B. IL is divided into two parts, one is capacitor current and one is load current, and as you know that IC doesn't support average current, so the IL average will be I0 when S is connected to B. Hence, the total average current through the inductor IL average will be given as IS plus I0. So, I have represented by the dotted line in the IL waveform the IL average part, which divides IL into two equal halves, and the peak to peak ripple is considered as del IL. Next, we will find the average value of currents IAS and IBS. We know that when S is connected to A, IAS flows, and during the time interval IAS is equal to IL, and we had already calculated IL average during the time interval, which came out to be IS. So IAS average is equal to IL average is equal to IS. And during the other time interval, that is when S is connected to B, if you refer the waveforms, IL average came out to be I naught, and hence IBS average also is equal to I naught. Thus I have represented IAS average by a dotted line in the waveform as IS, and for IBS average the dotted line has a magnitude of I naught. Next we will calculate the value of IC. When S is connected to B, if you observe the circuit and apply KCL, what you will get, IBS, the current flowing from B to S, is nothing but IC plus I naught. So from here IC can be written as IBS minus I naught. So in order to represent IC in the waveform, what we have to do is, we have already the waveform for IBS, and we will decrement that IBS by its average value I naught and draw it for IC. Hence I have drawn the waveform for your IC. During the DT period, what is the value of IBS? 0. So if you substitute in the equation, you will get IC is equal to minus I naught, and since I naught is a constant DC voltage, I have shown it as a straight line. So during DT period it is minus I naught, and during 1 minus DT period the IBS is decremented by its average value I naught. Next we will replace the single pole double throw switch by a MOSFET and a diode. Please recall the previous concepts that I have taught you and apply it over here. Since IAS is positive and VAS is positive, the device that is to be connected between A and S is a MOSFET. And if you observe IBS, it came out to be positive, and VBS is coming out to be negative. So between B and S, a diode is to be connected. Hence I have replaced the single pole double throw switch by a MOSFET and a diode, and a complete buck boost converter with all the switches and power electronics devices looks like this. So here completes the explanation of the circuit along with what are the components that are to be used in order to build a buck boost converter. Next we will be deriving all the necessary equations that will help you in solving the problems. So now we will write down all the necessary equations for a buck boost converter. I will not be deriving each and every equation step by step, because if you follow through my previous videos, you can understand how the derivation is done. So I expect you to derive it on your own. So let's start with the input output voltage relationship. So in order to find out the input output voltage relationship, we have to apply volt amp balance to VL. So applying volt amp balance to VL, VI is during the DT period. So VI into DT and V0 into 1 minus DT areas will be equal. So from that you can find out V0 comes out to be dVi by 1 minus D, where V0 is your output voltage and Vi is your input voltage and D is your duty cycle. Now how the converter operates in either buck mode or boost mode, it all depends upon how you choose your duty cycle. So if D is between 0 and 0.5, if you choose a value, suppose 0.4, so V0 can be given as 0.4 into 10 by 0.6, that gives you 6.67. So input voltage was 10, output voltage 6.67, it is acting as step down converter. Now if you choose D between 0.5 to 1, suppose 0.7, so V0 comes out to be 0.7 into 10 by 0.3, that gives you 23.33 volt. So 10 volt to 23.33 volt, that gives you step up operation. Next we will derive the input output current relationship. This relationship is found out by making the converter 100% efficient. So V0 I0 is equal to Vs Is. So from there you can calculate it to be I0 is equal to 1 minus D into Is by D. So next, finding out the ripple current del IL through the inductor and the inductor value L. So we have to write the equation for VL. So VL is equal to L dIL by dt, and do the necessary steps to find out del IL is equal to D into Vi by FL, and L comes out to be dVi by F del IL. Next, finding out del Vc and C. During the dt period, it is a rectangle, so it is very easy to find out the area of IC during that period. So we'll consider that period and write down del Q is equal to C del Vc, and substituting all the required values, we will get C is equal to d I naught by F del Vc, or del Vc is equal to d I naught by Fc. Next, applying the boundary conditions for del IL and del Vc. The boundary conditions remain same again. So del IL is equal to twice I naught. Substitute the values accordingly and you will get the critical value of inductance LC as 1 minus d into R by twice F. Similarly, for the capacitor ripple voltage, del Vc is equal to twice V naught, the boundary condition, and Cc, the critical value of capacitance, comes out to be d by twice Fr. Next, the average and maximum value of inductor current. The average value of inductor current was calculated out to be Is plus I naught, and if you substitute the value of Is as d I naught by 1 minus d, which we had already derived, so you will get IL average as I naught by 1 minus d, and IL max is IL average plus del IL by 2, so it comes out to be I naught by 1 minus d plus del IL by 2. Next, the switch ratings. I have already replaced AS by SW and BS by D. So ISW is nothing but the average value Is plus del IL by 2, and Is was calculated out to be I naught by 1 minus d, and VSW, if you observe, it is Vi plus V naught. And lastly, the diode ratings. The PIV, if you observe, VD comes out to be Vi plus V naught, and ID will be greater than I naught by 1 minus d plus del IL by 2. Thus here I have come to the end of the lecture. In this lecture, I have completely explained you the operation of the buck boost converter, how it is to be operated in buck mode or boost mode depending upon the duty cycle D. I have explained you all the relevant waveforms, how to draw it and find the average and maximum values of the currents from there, and written down all the necessary equations that will be required for you to solve any buck boost converter problem. So I expect you to go through the lecture thoroughly, and if you have any doubt regarding any portion of the lecture, please do write down in the comment section of the video. And also I expect you to provide your valuable feedbacks so that I can improve more on the next videos that I will be posting on my YouTube channel. So I have explained you all the DC to DC converters and have derived the necessary equations that will be required to solve the problems addressing a DC to DC converter. So in our next lecture, what we will be doing is we will be using those formulas that we had already derived in addressing some of the gate problems. So please go through the previous 3 lectures which we had done on buck converter, boost converter or buck boost converter, and get through all the formulas that we have derived, so that while we are going into solving problems in our next lecture, you will find it really easy to do it. All the formulas that I have derived, those formulas will be only required for doing your gate problems, nothing else will be required. So please focus on all the formulas that I have derived. For those who are visiting new to my channel and going through this lecture number 5, for them I have provided the link to the previous lecture on the description of the video. Please click on that link to go to the previous lecture and study all the necessary DC to DC converters, so that it will help you in understanding its basic, and thereby you can solve any problems regarding to the converter. And again, if you like the videos that I am posting on my channel, please do not forget to subscribe to my channel so that you get updated with the new videos that I will be posting in the near future. Once again, thank you all for the support that you have shown. I will be coming up with my new video in a very short time. Until then, goodbye, stay home, stay safe.